Is it possible to make the average student as smart as Albert Einstein in physics? Let's start by examining three major reasons why current methods of physics instruction fail. 1. Physics concepts are abstract, and often students are given no visualization whatsoever of what they might look like. Concepts like voltage, current, resistance, magnetic fields, and capacitance are often not visualized at all for students. 2. When students are given visualizations of what physical concepts look like, they are usually incomplete and only visualize the concept, such as voltage below, in one context and don't provide enough visual examples in all the various contexts that are critical to visually understand a concept completely. So, for example, in this circuit, there's a visualization of voltage, and you can only see this visualization at one wire. You can't click on the resistors and see what that looks like. So it has a lot of gaps. There are some animations that visualize things completely, but it's generally just in one section. They tend to miss a lot of key states still. 3. Students are generally never shown visually or even verbally how one physics concept, such as voltage, relates to another physical concept, such as magnetism. And so all the spatial relationships between concepts are never visualized for students. This is a competitor's suite of physics animations, and if you notice, they're not integrated in any way. They're all shown in isolation. And the same goes for these iPhone apps. They're all isolated. So let's see, how does visual cognition relate to the evolution of learning in human history? And this is important background. In the beginning, humans are very visual creatures, and visions are a top modality, and we see things in our imagination, in our mind's eye. But in the beginning, we could only communicate that with language and very simple drawings, and really other people could not see what you saw in your mind. As time went on, we had more sophisticated language, and we had more sophisticated paper and writing utensils, but still, we couldn't really completely convey what we saw in our mind's eye to other people. Eventually, technology grew, and television was created, and we started to use that to communicate our vision, almost literally, what we saw in our mind's eye in our movies or in our news. If you go to the movie theater, you never expect there to be text on the screen and diagrams. You expect there to just be straight video. But unfortunately, we didn't really ever make the leap of using television in a very systematic way to teach, especially for science. As time went on, we got even more technology, even better visualization tools, but we still continue to use text and diagrams to teach, especially for science. And accordingly, the best scientists, what they see in their mind, their visual models of science concepts, they can be communicated using computer animation technology, and students can see what they see, but we don't use it. We don't use computer technology effectively to communicate the visuals that scientists manipulate themselves. We still tend to use text and diagrams. So most of the visual and spatial content of scientists' vision is lost when we're trying to impart science to a student, because we use text and diagrams and it's not visually complete enough. But now we have the technology, and using these visual cognition techniques that we go over, that I've invented and expand upon, you can take the scientist's vision, what they see in their mind's eye. I'm sorry about that, it's a flaw. And you can communicate it entirely to the student. They can see exactly what the scientist sees, and they can think at the level of the scientist, such as Einstein, or really the best physicists in the world, the best of any field. So it's time society caught up, and my company, Visual Genius Incorporated, will take us there and capture the spatial and visual information that's literally been lost over the centuries in so many fields. So let's get into our product. I've designed these interactive physics simulations. This one teaches electrostatic forces for a few years in my doctoral work, and I've researched it and researched the efficacy and what makes it work well and how well it works. This is another simulation I designed as an animation depicting blue spheres represent the voltage, and the current speed electrons move in a series and parallel circuit, and then click on any part of the circuit and see how those concepts are visualized. And then I also worked on this capacitor simulation they can use to observe charge in an electric field in a capacitor, and it's very visual and it's very complete. So what I like to do is take all of those concepts and integrate them into one visualization where a student can click on any part of the wire, and this is a wire, and they can see the voltage and current animation, and they can see the electrostatic force that drives that voltage. They can see the magnetic fields that are created from the electrons moving. So all these concepts are related. They can see how they are related visually. And this is a mock-up. This is the animated. It'll be better as I work on it. And not just these concepts I went over, but all of these concepts, all the major concepts in the electricity magnetism unit, which I've mapped out, I'm going to visualize and integrate into one model, which will cause for very clear, very efficient, very fast learning. So in our visual software, all concepts have symbolic representations, like wires or graphs or symbols linked to visuals. So everything is completely visual. For example, often in computer animations, they link concepts to other symbols, like here voltage and current are represented with arrows, or here magnetic fields are represented very abstractly with numbers and some very basic diagrams and too many equations, too many graphs. Those are visual, but they're very syntactic. They're not really concrete. So ours are very concrete visuals, very easy to see. And then two, our software uses this iteration technique where we take the visualizations we design for every concept and we iterate it throughout the entire model. And it's very important to make sure that the animations are always comprehensive and complete. So, for example, in my dissertation work, I took different parts of the neuron and I iterated them throughout a model of the neuron here, and I created an iterative visualization of the neuron, and that had very excellent gains in learning, and it's pretty profound, the results, and I have a paper on that. And three, all concepts that are iterated visually are linked together, they're all integrated. For example, in my neuron study that I'm doing, I had a molecular view of the neuron and I linked the two so you could move from one to the other. Just like in the animation I showed you, the student can click through many layers and everything's integrated together in the visual model. So all of this is backed by research I've been working on for a few years now, and the research is very good. It gets better and better with every study, but I really do think it's at the point now to make a strong argument for these visual cognition techniques and their power. Other techniques will be used as appropriate. So with our company's iterative, integrated conceptual physics visualization, students' understanding of physics will be exponentially better and exponentially faster. They'll learn incredibly fast because everything's so integrated and so clear. And they'll understand physics like Einstein did. Einstein was a very visual person who was very good at integrating information. It's very Einstein-like, the abilities that they're going to get. Learning physics and science is a national priority. The U.S. ranks very low in science internationally. We need to improve science education so the U.S. can compete. Our visual integrated physics modules will improve student self-esteem and sense of capability to learn science because it will make science easy and fun and interactive and immersive, and it will reduce disparities in terms of quality of education based on race, socioeconomic status, and gender, because it's a scalable, easily distributed, fairly cheap learning system of the highest quality available to all students via the web, and it will empower a new generation of U.S. scientists and scientifically minded citizens. All domains are made up of spatial and visual codes, especially math and science, so the key to unlocking genius-level intelligence is to engineer the student's spatial and visual understanding of these fields. So our physics educational product will create a learning method and technological framework for visual cognition techniques so they can be applied to many other fields to make students achieve genius-level intelligence at anything and everything, because they'll be so spatially aware of the concepts. So you can apply to calculus, chemistry, accounting, even law, learning language, anything. It makes our business model flexible and makes us able to pivot so we can respond to the market. If somebody doesn't respond well, we can pivot, use that framework and technology to build another really high in-demand product, and we'll always survive. We'll always find a way to make it work and be successful. Really quickly, I started with physics because biology is too detailed. Calculus is a little bit too much of a jump at first, and physics is something I've been studying. It's easily visualized. Painful for students, so it'll create a lot of buzz if they can learn it simply and learn it at the level of genius. And chemistry is actually another good field. It's important to have a good crosstalk in the company between the subject matter experts, the physics experts, the programmers, and the designers, which is me, and I think that's really key to the company. And it's possible to have multiple teams of people working on different chapters. That might be a strategy. Hiring different low-cost consultants like undergrads in physics or short-term programmers might be a good way to keep costs low in the initial stages. We're going to have a very lean startup philosophy where we create modules for various chapters we're integrating, and we sell them, get market update, reiterate, and when we make the new version, for example, here we're going to start with electricity and magnetism, do that model, iterate, integrate it, then release it for like a small iPhone app, get market feedback, and we'll use that when we make the next chapters of physics we're going to do, kinematics, and we integrate all that, and we do the same thing. So we release these mini iPhone apps over the course of a year and a half, and then we use that as market knowledge to make sure we're always responding to the market and reiterating, just like the lean startup philosophy that's so popular and efficient. The major market are college students are 400,000, and there are 1.3 million high schoolers who take physics. So if we capture 10%, we might be able to sell about 170,000 units. And since the visualizations are so striking and innovative and cause such extreme gains in learning, they're unprecedented, I really think we can capture that market. So we have the high schoolers, the college students, and also we have MCAT students, so we're going to try to reach them through, directly through our software apps and software programs, and through textbook partnerships. Our major competitors are small companies that make physics software, and mainly physics textbook companies that have supplements. In order to get into a good relationship with textbook publishers, we'll try to create a buzz to catch their eye. The potentials I still have to work on, but things you'd expect, like the bulk of it's money for programmers and money for subject matter experts, and then the average normal cost you'd expect from a tech startup. I just want to show the long-term vision is we start with physics and we do a great job. We create a lot of buzz by teaching in a way no one's ever done before. We'll get really rapid, great gains in learning, help a lot of students learn, and we can branch out to other scientific subjects like chemistry, organic chemistry. Accounting is a good subject. Language learning, computer programming will be fast and good. Calculus, statistics. We can branch into visual analytics and help visualize stock trade data, databases, server data, help visualize search engine results for Google or Lexus or Hoover's, and we can get into science informatics and help, it would be really great applications, bioinformatics and engineering. So lots and lots of opportunities. So these techniques can help scientists discover things, make better drugs, even cure cancer and AIDS. I mean, a lot of that is just being able to see the molecular structures. So this company can really help skyrocket innovation and scientific understanding. So that's a question, like when's the right time to break into these different markets and different educational domains? It's something we really have to think about, and it'll be a really key aspect of the business model. I really do feel this company has nuclear potential. To be honest, it's explosive. I think will cause explosive gains in learning, speed of learning, the depth of learning. It will grow explosively because it will create so much buzz because the product is so good and these techniques are so useful, so applicable, and I actually do think it will spur a shift in how society learns, and it is the potential to get into the billions in the long term. It's just, I think, is tons and tons of potential. So this is my presentation for Visual Genius Incorporated, where we will help you see the unseen. Thank you.